Continuing discussing rational functions, I want to talk about asymptotes of a rational function. Now, vertical asymptote is, these are like imaginary vertical lines, and when we draw them, we write them as broken lines to imply that they're not really part of the graph. So we'll start with vertical asymptotes. A vertical asymptote occurs when the function either increases or decreases without bounds as x approaches some real number. So an example of that, if you take a look at this function, this is a function here, and notice that as x gets closer and closer to this vertical line, looks like that's x equals 2, but as x gets closer and closer to it, notice that the graph goes farther and farther down from this side, and then from the other side, as x gets closer and closer to the graph seems to get higher and higher. So as you approach this number, we'll just call it 2 for now. So as x approaches 2 from this side, the graph decreases without bound, and as x approaches 2 from this side, the graph increases without bound. Okay, so that's what a vertical asymptote looks like. Now, a horizontal asymptote can occur when x approaches infinity or negative infinity, and the function actually approaches a horizontal line. So basically, if the function approaches a horizontal line, it approaches some constant. So take a look at the second example. In this example, notice that as x increases, in other words, as x approaches infinity, notice that the graph seems to level out near this horizontal line here. We'll call this horizontal line y equals 3. And so as x approaches positive infinity, the graph levels out at y equals 3. And as the graph approaches negative infinity, so as the graph goes negative, the graph also levels out at this same horizontal line, y equals 3. So that's what a horizontal asymptote looks like. Now, a slant asymptote is also called an oblique asymptote. These can occur when x approaches plus or minus infinity and the function approaches a non-horizontal line. So here, let me show you here. Notice as x goes to infinity, the graph continues to increase. But as it increases, it gets closer and closer to this slanted line. And that slanted line is called the slant asymptote. So those are actually the three types of asymptote. And by the way, as x goes to negative infinity, the line gets closer and closer to that same slant asymptote. So these are the three types of asymptotes that you would have in a rational function. Now, you can have a vertical asymptote and a horizontal asymptote in the same graph. I actually have one here, but I only talked about the vertical asymptote. And you can actually have a vertical asymptote and a slant asymptote in the same graph. This one actually does have a vertical asymptote. I just didn't identify it here. But what you can't have is you cannot have a horizontal asymptote and a slant asymptote in the same graph, because these asymptotes both come from when x approaches infinity or negative infinity. So if x approaches infinity and the graph levels out, then you get a horizontal asymptote. And if as x approaches infinity, the graph approaches a line, a slanted line, then you get a slant asymptote. And of course, you know, it's possible that x approaches infinity or negative infinity and you don't get either one of these as well, but we'll talk about that later. So that's some examples of asymptotes, and now I want to show you how to identify asymptotes. Okay, vertical asymptotes are the easiest ones to identify. To identify a vertical asymptote in a rational function, they will only occur at the x values that make the denominator 0 but don't make the numerator 0. Now you want to be careful there, because generally if a number makes both the numerator and denominator 0, then you actually get a hole at that point and not a vertical asymptote. So here at 1 over x, you get a vertical asymptote at x equals 0 because x equals 0 makes the denominator 0, and of course it doesn't make the numerator 0. And here's the graph of 1 over x. And notice I tried to draw this, but the axis kind of obscures my line. But if you look real close, you can see there's a red broken line that goes through the axis here, and that line is actually the line x equals 0. And so you notice that as you get close to x equals 0 from the left, notice the graph continues to decrease, and as you get close to the right, notice the graph continues to increase. So, if I back out a little bit, you can probably see it a little better, that you would get a vertical asymptote there at x equals 0. Now on the second one here, we also know that if x equals 2, the denominator is 0, and of course the numerator would not be 0. So we would get a vertical asymptote at x equals 2 for the second one. So if we look at the graph of this one here, notice here that here's x equal 2. This is the vertical line, x equal 2. And notice that as you approach 2 from the left, notice that the graph decreases without bound, and as you approach 2 from the right, the graph increases without bound. So there's your vertical asymptote there. Now remember, on this third one we found that the denominator was 0 when x equaled -5 or 5. And obviously these values don't make the numerator 0, so we would get vertical asymptotes at those values at -5 and 5. And if you look at the graph of that, you can see here is the vertical asymptote at, hang on just a second, let me turn that off. Alright, so here's the vertical, well the red is the graph, but here's the vertical asymptote at x equal -5. And notice as you approach -5 from the left, the graph decreases without bound. As you approach -5 from the right, the graph increases without bound. Well, this graph actually has two vertical asymptotes because you also have one at x equals 5. And as you approach 5 from the left, notice the graph decreases without bound, and from the right, the graph increases without bound. So you actually have two vertical asymptotes for that function. You can actually use a little trick to identify horizontal asymptotes. And horizontal asymptotes occur when the degree of the denominator is less than or equal to the degree of the, I said denominator. They occur when the degree of the numerator is less than or equal to the degree of the denominator. Now, notice I said less than or equal to. So let's talk about the less than case. If the degree of the numerator, remember that's the top, is less than the degree of the denominator, the horizontal asymptote is simply y equals 0. In other words, the x-axis. So let's take a look at three very similar graphs, and let's see how the vertical asymptotes change. So if you take a look at this function, f of x equals 2x minus 1 over 3x squared plus 2, you'll notice that the degree of the top is 1. Remember, this has an exponent of 1. So the degree of the top is 1, and the degree of the bottom is 2. So in that case, the degree of the numerator is 1 less than the degree of the denominator. Therefore, the horizontal asymptote would be the line y equals 0, which is the x-axis. So on this graph, here I've graphed the function. So notice here that if you let x get large, in other words, if you let x go to infinity, notice that the graph gets closer and closer and closer to the x-axis, which is the line y equals 0. Now this also happens in the negative direction as well. So as x gets very, very negative, the graph gets closer and closer to the x-axis, y equals 0. So in that case, the x-axis, which is the line y equals 0, serves as the horizontal asymptote for that graph. Let's look at the next case. If the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the ratio of the lead coefficients. So look at the second example here. Here, the degree of the numerator is 2. The degree of the denominator is 2. So therefore, we have case 2. So in that case, the horizontal asymptote is the ratio of the lead coefficients. So the ratio of the lead coefficients, that would be the highest degree term. The highest degree term on the top is the 2x squared. The highest degree term on the bottom is the 3x squared. And the ratio of those coefficients would be 2 over 3. So in this case, I would say, since the degree of the top and the degree of the bottom are the same, I could say the horizontal asymptote is simply the line y equal 2/3. Let me show you that with the graph. Here's the graph of this function, and this dotted line right here is actually the line y equal 2/3. And you'll notice that as x goes to infinity, this graph gets closer and closer and closer to 2/3, and also as x goes to negative infinity, the graph gets closer and closer and closer to 2/3. So you can see that y equal 2/3 is the horizontal asymptote for that function. The last case for the horizontal asymptote is if the degree of the numerator is greater than the degree of the denominator. There is no horizontal asymptote because the function either continues to increase or decrease as x goes to infinity or negative infinity. So let's take a look at this one. Notice here the degree of the numerator is 3, the degree of the denominator is 2. So in that case we would have no horizontal asymptote. And let me show you a picture of that. See, on this one, let's get rid of that previous line. Okay, so on this one, as x gets large, the y values, so as x increases, the y values just continue to increase. And also, as x decreases, the y values continue to decrease. So there's no leveling off for this function, so you get no horizontal asymptotes there. So I'll reserve the slant asymptote discussion for the next video, and it depends on your instructor whether or not you need to spend a lot of time on the slant asymptotes, but I think it's important to at least know what a slant asymptote is.